Thank you very much for giving me this opportunity to talk about one of my favorite topics, fusion energy and the Wendelstein 7X stellarator. So here's my overview. What is plasma? I'm going to talk about that, and I will explain to you what is fusion and what is the potential of fusion energy. There are two leading fusion concepts, the Tokamaks and the Stellarator. I will talk about both. And then I'll show you what progress we've made towards net fusion energy production. I'll then introduce the optimized stellarator, Wendelstein 7X or W7X, which is the device I'm working on, and give you a few of our first results, which were obtained at the end of last year, but most of them this year. How much did W7X bring us closer to fusion energy so far? You can actually quantify that and put it on a graph, and you see where we've gone and where we need to go. Also, where we expect to go with this device in future operation phases. Finally, looking towards the future after W7X, what would a stellarator power plant look like? And then I'll summarize. Okay, so plasma is the fourth state of matter. If you take the temperature and increase it, you start with solid state. Think about ice, for example. And you warm it up, it begins to melt, it becomes a fluid. The molecules move between each other, but they're all touching each other. If you keep warming up water, it begins to boil, you get gas. But not, you don't stop there. If you keep increasing the temperature, what happens with those molecules and atoms is that there's enough energy in the system at a temperature of something between 10,000 and 1,000,000 degrees that the molecules and the atoms break, the electrons become free, and you have a soup of free electrons and free ions. This is now an electromagnetic gas. It can conduct electricity, it can react to magnetic fields, unlike a regular gas, which has very little interaction with electromagnetic fields. So we don't have that many plasmas on Earth, but you've seen some when you've seen lightning. That's basically a plasma that's created from atmospheric air by the enormous voltage difference between a cloud and the ground that creates enough energy to create a thin plasma that conducts the electricity and thereby releases the charge in the cloud. There's also northern lights where plasma coming from the sun gets guided by Earth's dipole magnetic fields towards the poles, the North Pole or the South Polar region, and you can see this lighting up the upper atmosphere. Now, fusion and fission are both nuclear forms of energy, but these are the opposite processes of each other. Fusion works by taking light elements and making them larger, whereas fission takes the super heavy elements and breaking them into smaller elements. And you can release energy on both sides of this scale. Somewhere in the middle, around iron and nickel, there is no more energy to be gained. But on both sides, and you can see here clearly on the fusion side, there's a lot of energy to be gained, but there's also quite a substantial amount on the fission side. But these are two very different processes, fission and fusion. Fission requires neutrons that multiply and break more and more nuclei, and you have a critical mass, whereas fusion requires high temperatures. You have a critical temperature for your process. But you don't need to have an enormous amount of material. The most important elements for fusion are the isotopes of hydrogen. So we have the proton, the regular hydrogen, and then we have deuterium, which has an extra neutron, and we have tritium, which has 2 neutrons. And if you take deuterium and tritium and you fuse them, you get helium, and you get a rather large amount of energy released. So we can look at it like this. We need about 20,000 electron volts. That's about 200 million degrees. for tritium and deuterium to overcome the Coulomb repulsion. They're both positively charged, these nuclei, and they need to come close enough that they can feel the strong binding forces and become a new nucleus. This lives for an infinitesimal amount of time, spits out a neutron, and becomes basically helium. So the ash of our process is helium, and the fuel is deuterium and tritium. Tritium does not exist in nature. It has about a 12-year half-life. It can, however, be created inside the reactor with this process from lithium. Here's the idea. That neutron that's created in a fusion process can be used to split lithium into tritium and helium. And so this tritium is created from lithium. So what you bring into your power plant is deuterium and lithium. And inside the power plant, tritium and deuterium is burned to create helium. And so in the end, the ash that comes out is helium, and what we bring into the power plant is deuterium and lithium. And this is really an enormous amount of energy that's stored in this process. It also has an enormous amount of energy density. If you just had 800 grams of deuterium-tritium fuel, that would release as much energy as burning 10,000 tons of coal. Deuterium exists in seawater at a concentration of 0.015%. Doesn't sound like much, but I'm going to show you it's a lot. Whereas, as I said, tritium must be created from lithium in the reactor with this process. And so, to give you an example from everyday life in some sense, if you take the amount of deuterium that you find in water in a bathtub and the amount of lithium you have from a single laptop battery at home, you'll have about 50 years of energy for a typical family. And I'm going to show you now that there won't be a lot of equations here, but I'm going to do a little bit of math here to convince you that we have energy for 1 million years stored in our oceans. The world energy needs today are 157,000 terawatt hours per year. Now, as physicists, we like to go into SI units, so I convert this into joule, 5 times 10 to the 20 joule per year. In the future, I expect us to want to use more energy than we do today globally. And so let's multiply that by a factor of 10. And then let's look at the energy density of the deuterium-lithium fusion fuel, which is the stuff that's coming into our power plant. That's 10 to the 14 joule per kilogram. Then you can take one divided by the other and come to the conclusion that global fusion fuel use per year will be about 50,000 tons per year. So this sounds, at first, 50,000 tons. Maybe that's a lot, maybe not. Well, as I said, we have 1 million years worth of this in the oceans. So let's multiply this by 1 million and say that there should be 5 times 10 to the 10 tons of fuel if I am to convince you about this 1 million years. The deuterium inventory in the oceans is about 1.5 times 10 to the 11. So this is more than a factor of 2 more than what we need. And the lithium inventory is similar. So it also has actually a bit on top for 1 million years. The ocean volume would shrink by 0.03%. And mind you, this would happen over 1 million years. So this is not something we need to worry deeply about at this point. So we will literally be able to extract fuel for our fusion power plants up to 1 million years. And it gets better in some sense. There are other fusion processes that await. You can do deuterium fusion that still requires this volume of fuel, but you can also imagine going to the moon, harvesting helium-3. There's actually a proton-boron-11 fusion process, which is very difficult to reach, but if we can make that work, that's also a fuel we can use. It has a lot of advantages, but it's much more difficult than the deuterium-tritium process. But what we need is a temperature that's on the order of 100 million degrees. And that's actually 10 times hotter than the core of the sun. The nice thing about these plasmas is that they're much thinner than air. They're 100,000 times thinner than air. But nonetheless, we must avoid contact with material objects so that we can reach 100 million degrees. And we do that with magnetic fields. Because our plasma is charged particles and they react to magnetic fields, they gyrate around magnetic field lines and they free stream along the magnetic field. So we get confinement in the sense that a particle will gyrate around a field line and will not move across the field lines unless it has a collision with other particles. And then it will take a step that's on the order of this radius. But along the field, we have no confinement. The particles will just free stream along the field. That this actually works, that magnetic fields can confine plasma, is actually something you can convince yourself of by just looking at the sun. This is an eruption on the sun where plasma is being created on the surface accelerated, and there's a magnetic field created in the process also that guides that plasma back towards the surface. Now, the surface of the sun itself is plasma, so you can sustain this process even though you end up going back into the surface of the sun. We need to do something a little bit different to reach our very high temperatures in the laboratory. We want to make sure that the parallel free streaming does not make us lose the particles. And we can do that in a torus, like a tire tube. In a torus, there is no loss of particles or energy in the direction of the magnetic field. The particles will just gyrate around and come back in that same volume. And what we can do when this works, okay, all right, it works on my screen. What we can do is make the magnetic field such that it creates these nested surfaces. So each of these surfaces contains plasma at a particular temperature. The plasma can flow freely along the field on the surface, but it has a hard time reaching the next surface. And this means we can have a high temperature of plasma in the core and a lower temperature as we go out. We can have 100 million degrees in the center, and we can have something like 1 million at the edge. And that still sounds like a lot, but remember, it's 100,000 times thinner than air. We do have materials that we can contact plasma at 1 million degrees. And the plasma isn't cooled off dramatically by that. And so these toroidal magnetic concepts come in various flavors. The two leading ones are the Tokamak and the Stellarator. And so what you see here on the left is a Tokamak. It's axisymmetric. It doesn't change its shape or form in the toroidal direction this long way around. The magnetic field from these blue coils here, these coils, creates a toroidal magnetic field that guides the plasma in that direction. You need a current also inside the plasma to create a poloidal magnetic field component. And together they have a twisting screw pinch-like configuration. This requires then that a current runs in a circle. So you can't just have a voltage from A to B. You need the current to keep running in a circle. You can do that by transformer action, but that means that it's pulsed operation. You can use the transformer to go in one direction, but at some point you need to reverse and go back, and at that point you lose your plasma. But you can also make this twisted magnetic field by twisting your coils instead. And this is what we do in the Stellarator. And by having twisted coils, we can have continuous operation, continuous confinement of the plasma. Now, the Tokamaks are at the moment still ahead of the Stellarators, and so these pulsed operation devices have had the best performance so far. I'm going to show you our best fusion power performance to date. This is from JET, which is an experiment in the UK. You see here a picture of jet, and we've put in what it would look like with plasma in it, and a person for scale. And here's some data showing that we reach 16 megawatts of fusion power for something on the order of a second. However, this was done by heating this with 25 megawatts. So you heat with 25, you get 16 extra, you get 41 megawatts of heat coming out. That's actually not enough for net energy production, because heat at 41 megawatts is something you can convert to maybe 15 or so megawatts of electricity. And you already used 25 to heat it up. So this is not a winning game. You need to have better performance than that, but it shows that the principle is correct, and these results were in line with our expectations. So what we are doing with the Tokamaks is that we're scaling them up. The next device in the Tokamak line is called ITER, which is a larger version of the existing one. So you saw a picture of jet before. Then you have to imagine scaling up to a substantially larger scale for ITER, which will have a multiplication factor of the heat of a factor of 10. So 50 megawatts of heating will give us 500 megawatts of heat. So this is the goal of ITER, to show that we'll get 10 times power amplification. As I said, 500 megawatts of fusion power for 50 megawatts of heating. It has a 6-meter major radius. It's not built yet, but it's under construction in France. You see a person here. It's a very large device. And so we are making progress, but we have been at this for a long time, and there is a joke in the community that fusion is the energy source of the future and always will be. We keep claiming it's going to come, it's right there around the corner, and then it takes a bit longer, and then we say, well, we need to build a new device, and then we'll make it. So indeed, fusion has been an elusive goal, but are we making progress along the way, and how rapidly? When will our fusion fire burn by itself? So what does that mean, burn by itself? Ignition occurs when the fusion process itself heats the plasma enough that it stays hot despite the inevitable losses that you'll have when you have something that hot right next to room temperature. So what we want is that the self-heating exceeds the self-cooling of the plasma. The fusion energy production in the volume of this hot plasma is proportional to the fuel densities, deuterium and tritium, both of them. So it goes like the square of density when you increase both together. And it's approximately proportional to the square of the temperature. This is an approximation, works in this temperature range. But it's a good approximation because we have a simple formula now for fusion energy production. It goes like n squared T squared. We have a way of quantifying the self-cooling in terms of the inverse of the energy confinement time. So tau, the energy confinement time, is the time scale over which the plasma cools off if it isn't heated. So this inequality can be written as the fusion production times, and this is per unit volume, so per cubic meter or something like that, times the volume, must be greater than some constant that depends on complicated physics that I'm going to gloss over. You can ask me at the bar. And the energy content in the plasma, which is basically density times temperature times volume, and then you divide by this time scale over which that's disappearing. So the shorter the confinement time, the faster the plasma is losing its heat. Okay, but this is an equation that we can solve fairly easily. We have some squares that disappear, and all these actually disappear. The volume drops out. It was on both sides of the inequality, and we can multiply the energy confinement time over on the other side. And what we find neatly is that all we need to do is to have the density times the temperature times the energy confinement time larger than this constant. And this is in the units that we use in plasma physics, 4 times 10 to the 21 per cubic meter kiloelectron volts seconds. Okay. So, what does that mean? How close are we to that? So this is our triple product, n times t times tau. It's been normalized so that this is where we need to be to make net energy production to have an ignited plasma. And these are all different experiments conducted in the 60s, 70s, 80s, and the 2000s. So you're seeing progress towards this goal. The other parameter that I'm plotting here is the temperature in millions of degrees, because remember, this approximation of t squared only works for temperatures that are on the order of 100 to 400 million degrees. And in fact, we've reached those temperatures. We've, in fact, even exceeded them in some cases, some of these experiments. We have even exceeded the densities required for a fusion power plant in this Stellarator in Japan. But remember, it's the product of all three simultaneously that needs to be achieved. And that's what we've got on this scale, and we're not there yet. We're hoping to get there, or very close to it, with ITER, but we're not there yet. But remember, this is a logarithmic scale, so we've actually made progress orders of magnitude in this parameter. So let's compare this on a time scale. How much have we improved the triple product as a function of time? And let's compare it. Let's ignore the green curve for now, but just compare it to processor speed in computers. Moore's law, this amazing ability of the computer to be twice as fast every 2 years. We've actually been doing the same kind of thing with the triple product. We are neck to neck in some sense with computer power. It's been doubling every 1.8 years, although you should now notice that it says 2005 here, and I'm not plotting further on, so there's got to be some bad news that I haven't told you about. It sort of is. The next device that would take us up here would have been in 2005 if this ITER project had been turned on in 2005. So why is ITER not yet ready? Why is it sometime in the future? The big difference here between what I just said about computers and fusion energy is that free market forces drove the development of the computers, whereas fusion strongly depends on public funding. We don't have a product yet. We're not producing net energy anywhere along this. This is only when we reach this point. So let's see how this plays out for ITER. In fact, the ITER science concept was already back in 1979. People were talking about having such a device. In 1985, Gorbachev, Mitterrand, and Reagan agreed in Geneva to build ITER. So we were looking like we were on track for this. There were some design and cost estimates in the 90s, and in 98, it was decided that ITER would be too expensive in its form that had been designed. It was estimated at the time at about 10 billion euro, and this was simply too much. We lost the political support for this, and we had to redesign it. In November 2006, there was a smaller version. This was approved. We had learned some things, obviously, in the meanwhile, that also, some of them allowed us to make a smaller version that had almost the same kind of performance. And the detailed design studies could begin in 2006. This is done by 7 international partners: the EU, China, India, Japan, Korea, Russia, and the US. And they have now agreed fairly recently which components are contributed from which partner. It's a complicated process, but the delivery started in 2014. But you see, we're beginning to go off that scale. We're now at least 10 years behind that earlier graph there. If you want to learn more about ITER, this is the website for ITER. So, in the meanwhile, why are we beginning to study the Stellarator again with extra force? The Tokamak has, as I said before, must have a strong toroidal plasma current. There's a strong current running inside the plasma. Whereas the stellarator doesn't need to have any current running in the plasma, but the plasma itself tends to create some toroidal current. This means we need to drive this in the tokamak, and this might actually require several hundreds of megawatts to sustain the millions of amperes that are needed in the plasma in a tokamak. Whereas we don't need that in the stellarator, and this will give us a much lower recirculating power. We don't need to use part of the fusion power to drive the current. We don't need to drive current. The plasma creates a little bit. We don't care much about it. So where are the drawbacks of the stellarator? This comes about how well the plasma is confined. A tokamak has excellent plasma confinement, whereas the excellent plasma confinement in the stellarator still needs to be demonstrated. It has been behind the tokamak in that respect for decades. On the other hand, the strong current is not just a problem in terms of current drive, it's also the source of plasma instabilities that may disrupt, basically wipe out the entire plasma in a very short amount of time. Whereas the stellarator plasmas are very stable, and as I said before, we can operate these plasmas in steady state. So if you want to think about it like confining water, the tokamak is like a water-filled balloon. It holds the water very well, but it may spontaneously just break, just pop. And the stellarator is like a water-filled bucket with holes. It's leaky, but it doesn't break. But it might be too leaky. That's the problem. But we know now how to plug the holes. That's my claim. So what are these holes? Well, there are particles inside a plasma that is confined by magnetic fields that follow the magnetic field lines faithfully. And those particles are well confined in tokamaks and stellarators alike. But some of the particles that have a lot of perpendicular kinetic energy, that do a lot of gyration and not so much back and forth, they actually get reflected off the high field regions, which I'm showing you here in red and yellow. And they don't go all the way around. They bounce back and forth, and if it's back. They bounce back and forth, and they drift away if you're not careful about how you created the topology of your magnetic field. So this particle started out at maybe 50 million degrees temperature and a hot place, and then it drifted out and hit the wall in a very short amount of time. Okay, now let's look at W7X. This is an optimized configuration. We've used computer codes, we've developed equations to help us keep the particles in. These particles that circulate the entire way around, they're always well confined also in our device. It's these bouncing particles where you have to be very careful about the magnetic field and its topology and how the magnetic field strength changes on this surface. And if you do that right, you can see you can get the particle to stay in the region where it was born at the temperature it was born, and you don't lose the heat. So this is what our computer codes tell us. We've built an experiment to prove that it's also correct. And that's W7X. So this complicated shape that was created by computer optimization is a total of 30 cubic meters. The plasma mass is only less than it's about 1/10 of a gram. This is really just, keep that in mind, that the amount of fuel we have in a fusion power plant is tiny. The magnetic field is up to 2.5 Tesla in operation. In fact, the coils can go up to 3 Tesla. These coils have crazy shapes, if you will, but these have been calculated also by computer codes. So we started out by saying the magnetic field should look like this, and then we asked Maxwell's equations, what should the coils look like? And the computer code said, these coils will create that magnetic field. In total, we have 70 superconducting coils, and they're enclosed in a cryostat at 4 Kelvin, minus 269 degrees. And so there's a lot of piping and cooling inside of that cryostat. And the cryostat itself is its own little vacuum vessel. You need a vacuum so that you can make things that cold. And this is the outer part of the cryostat beginning to appear. In total, we have 435 tons that get cooled off to 4 Kelvin, and 735 tons in total once we've closed the cryostat. This should make plasmas that we can make last for 30 minutes. In principle, they could go on for weeks, but there's a limit to how much cooling water we have. And we'll have a heating power of 10 megawatts to create the plasma, or in pulses up to 20 megawatt. This is what the device looked like during construction. So you can see this toroidal shape and a lot of ports and a lot of complexity. So let me just show you a little movie that takes 9 years of construction and puts them together in about a minute. And we can talk a little bit while you look at the movie about the different components. So what you see here is the vacuum vessel that contains the plasma. Remember, there's a vacuum vessel outside of it that will contain the coils. You're seeing coils arriving. Because of their complicated shape and the complicated shape of the plasma and the vacuum vessel, all of this had to be calculated carefully in CAD programs to ensure that we were actually able to thread them on properly and by what angles we had to do this. But that all worked out nicely. W7X has 5 identical modules. Each module has a mirror image half module, two mirror image half modules. And so we have in total 10 half modules, 5 full modules. And what you're seeing here is a full module being finished up. Now it's finished, and it gets moved into the torus hall where the experiment will begin to take form. First, we put down the outer shell of the cryostat, and then we put in this module, and then we put the upper shell of the cryostat on, came there. And then 1/5 of W7X has been completed. Now we're looking from the top, you're seeing more components appearing. The other modules are beginning to appear one by one. And I'm showing you this also partly to just show the complexity of what we're doing and the amount of engineering and engineering accuracy that is needed to build together a real experiment out of a computer that solves complicated codes. I'm sorry? It what? Oh. All right. Well, anyway, the device is finished now. This is what it looks like on the inside. It's also complicated on the inside. These things will be cooled in operation, and they will all have graphite tiles on them because graphite is a very good high temperature material. So it's a complicated device. The first thing we did was to confirm that the magnetic topology is what it needed to be. What we need is to have these nested magnetic surfaces. Okay. What we need are these nested magnetic surfaces, one inside the other, a single field line tracing out one of these surfaces. Okay, and how do you actually measure that? There's no plasma needed for this measurement. What you do is you send an electron beam along the magnetic field, and the electron beam moves at 1,000 kilometers per second along the magnetic field line, round and round, many, many times, and it basically maps out a magnetic surface. See if I can get it to, okay, go quick. All right. So if you take a rod and stick it into this electron beam, it lights up, and you can basically, by sweeping the rod through the plasma, get this shape that you have a hollow magnetic surface. This is what it really looks like when you do this in real life. And if you then move the egon, you can see that there are other surfaces inside and outside of this surface. In total, if you do a little bit of background subtraction and clean up your photos, you can get a whole image of these nested magnetic surfaces. These will be the surfaces with the highest temperature, and these are the ones with the lowest temperature. You can even see little bubbles in these magnetic surfaces. We call these magnetic islands. We'd calculated these ahead of time, and they were exactly in the locations that we expected them to be. So this was a good confirmation of the accuracy of the device. You can even visualize these magnetic surfaces by having a little bit of background gas. Then you can actually see the electron beam, and by that, see the magnetic field lines themselves light up. And so we're looking into one of these hollow magnetic surfaces here. You can even use both methods, this method with the rod and the visualization of the field lines together, and get some beautiful photos that you can make sure that the public appreciates what you're doing. So, our first plasmas. We were actually technically ready for first plasma in July 2015, so over a year ago. But we still did not have an operation allowance. On December 9, 2015, we received it, and the day after we created our first plasma. This was made of helium, and the plasmas that we have made until now have all been created by microwave radiation. That's the heating source we use. The very first plasmas reached about 1 million degrees Celsius in the center. And we had press and TV crews from many parts of the world present, also broadcast the event live on the internet. And maybe, since we're in Denmark, you may have seen the feature on the TV2 late news, where they spent a good 7 or 8 minutes on fusion, which was, I think, maybe a world record. Thank you. But our first plasmas actually died a quick death. Let me just show you one of these. This is a movie, which is hopefully going to play. I think so. You see something starting in the center and then expanding out. And then it begins to radiate a lot at the edge, and it shrinks and it dies. If you look at the time scale, we're talking about it living for less than 100 milliseconds. So this is also less than 1 milligram of helium, so it's not a whole lot. But what happens is that we have created a plasma by depositing energy in the center. I'm going to run the movie again. And then the plasma expands from the center and out and fills the flux surfaces that you saw before with hot plasma. What happens, though, simultaneously is that the temperature gets so hot that the plasma stops radiating in the visible, and the camera can't see it. That's why it becomes hollow. And this is actually indicative of a high temperature that we don't see any radiation with our regular cameras. The plasma will radiate in the ultraviolet and in the X-rays. And what happens when the plasma collapses is that the plasma radiation provokes molecules that are on the walls, in particular water vapor. It provokes water vapor to come off the wall and stream into the edge plasma, and it basically overfeeds the plasma with particles. They radiate all the heat away, and the plasma cools and shrinks. But it also cleans the walls. The positive side about this is we're cleaning the plasma walls. So we just did these over and over again, and they began to last longer. They would last longer than 100 milliseconds. They would approach half a second, and at some point we decided, let's go from helium to hydrogen. The nice thing about helium is that it's an inert gas. It doesn't stick to the wall. It has no chemical reactions. It's perfect for cleaning. But at some point, you need to go to hydrogen. Remember, the hydrogen is the fuel of fusion. And we thought that we could ask Angela Merkel to create our first hydrogen plasma. And she indeed came. And so I'll show you a little movie of that.
Take 60
see in our
seconds.
control room.
And you will see in the screen there, and we'll see up here the first hydrogen plasma. So, Chancellor, press the button. There we go. Wonderful. You've done it. So the countdown is on.
Right. So now they're all looking and they're like, oh, there's no plasma. What's going on? No. The way we make plasmas is we press the button and then it takes a whole minute before we actually try to make the plasma. And that's because we need to get all the laser systems and the heating systems to warm up and be ready so that you can heat the plasma, you can measure the temperature and density of the plasma. That all takes preparation, and that runs automatically on a 60-second clock.
Counting down. I wanted to be able to see it here, so in a minute it's ready to go. Any minute, any second, as it were.
There it was. And everybody's happy. There you go. Thank you. So these are the things that make you nervous as a scientist. Is it going to work this time? With so many people looking, it seems like you're just asking Murphy's Law to give you trouble. So that was at a point where we were able to make half-second pulses, but actually at some point we managed to reach a second. This might not seem like a lot, but it's a milestone. It's an SI unit. And for what we had expected for this operation phase without cooled walls, this was pretty good. We actually reached 6 seconds later on. But this plasma also reached 100 million degrees, which is also quite impressive, of electron temperature. One interesting thing about plasma is that because it's so thin, you can have the electron and the ion temperature be vastly different, even though they're in the same volume. They just don't transfer the heat between each other efficiently enough. And we're heating only the electrons with the microwaves. So in fact, the ions were a factor of 10 colder than that. Okay, so let me switch to another topic that is very important for fusion and has caused us problems predicting how quickly we get to ignition in the past, and that's turbulence. Tokamaks and stellarators alike suffer from turbulence in the plasma. This is not a major, huge problem, but it does mix the plasma faster than we thought in the 50s and 60s. These turbulent structures are highly field-aligned, and we can calculate them rather accurately today and also calculate their effect on confinement. So let me just show you a little movie of a simulation of plasma turbulence in W7X. And what you notice is that these are pulsating long filaments of increased or decreased temperature or density of the plasma, usually both things at the same time, mostly density. And this pulsating and sometimes rotating is actually something that we can see with special cameras. It's visible at the plasma edge. Remember, the core of the plasma gets too hot, we can't see any radiation in the visible. We can't see anything now. Hopefully it'll come back. Yes, there we go. Plasma emits visible light as long as its temperature isn't too high, so on the order of 1 or 2 million degrees. And at the edge, it's cold enough that we can actually see some of these filaments. And we have a fast enough camera to resolve the plasma turbulence. It takes 46,500 frames per second. So it's a scientific camera. And it's a complicated view, however. I'm just showing you this mess of magnetic field lines to convince you that it's, you can kind of make a little bit of sense of this. So when you see structures like this, it means that they're mostly aligned along the magnetic field, and you're looking into this hollowness that's just looking into the hollowness of the hotter plasma. And so let me just run that little movie by you. You can see this churning and rotating mess of filaments. And what you're looking at here is actually only 2.5 milliseconds And we didn't even last that long. 2.5 milliseconds of turbulence. It's going to come back. I know it now. Yeah. Let's try it again, see if it stops working. So you see this rotation. Now, this turbulence was also measured by magnetic sensors, so-called Mirnov coils, particle sensors, so-called Langmuir probes, microwave sensors, something we call Doppler reflectometry. We have a lot of physicists who get their names up on view graphs by developing diagnostic systems. Okay, now I'm going to summarize what we've achieved in this first phase. There we go. So this was a 3-month operation phase. We managed to put twice as much energy into the plasma as what we thought we might be able to, given that we weren't cooling the walls. We reached up to 6-second discharges. The heating power was close to what we had expected. We didn't want to push that system. We could have, but there was no particular need for it because, in fact, the temperatures were much higher than what we had conservatively estimated beforehand. Even the densities were somewhat higher. And this energy confinement time I talked about before was about 100 milliseconds, which actually isn't bad. It's pretty good. Now, in the next phase, we want to get much larger pulse energies because we will have a better exhaust system. That's what's called a diverter that exhausts the heat in the particles out of the plasma. We didn't really have that in the first phase. We'll have more heating power, and we expect to get similar temperatures that we did in that first phase, but substantially higher densities. And in a, let's say, final, not hopefully final phase of operation, but the final one in our plants at the moment, we will go to 18 gigajoules, 10 megawatts for 30 minutes. This is what I promised on an earlier slide. So this is something we will be able to do in 2020. More heating power, even higher densities. So that's where we're going. But what do these results mean in the bigger fusion picture? There's a lot of impressive numbers here, but how close are we really to making net energy with a stellarator? So let's compare to what's already been done. Again, this is our triple product, this is our ion temperature, and this is what we achieved. So we have left a few other experiments behind already, but we still need to do a lot of catch-up. For the next phases, we expect to get up to these points, where we will also be at the level of large tokamaks like JET that I showed you before. Not so much in terms of temperature, but in terms of triple product, we're already doing pretty well. There's still a way up to the very best tokamaks, and in fact, we need another generation of stellarators to close that gap. Another way to look at this, though, is to plot the triple product against the plasma duration time, because our plasmas in the stellarators are steady state. And so we can go to plasma durations that are much longer than the tokamaks. And so this is what we achieved, this is what we expect to achieve, and you see we're actually going into uncharted territory in future operation phases with our device. And you can see that the tokamaks are sort of on a path to a pulsed reactor that can make a plasma for a few hours at a time, whereas we're on track for making a steady state reactor. In fact, you can kind of drive home that point by arguing that if we had a cooling tower right by our institute and we upgraded our microwave system, we're not planning to do either one, but if we were to, we would be able to extend the pulses to practically as long as you bother, if you will. You will probably end up with some erosion of the walls, some interesting physics program on that. But the point is, we can go in this direction with this device, and what we need to show is that we can go in that direction as well and reach this step. So how would we do that? We would have to build a bigger device, a rather substantially large device. This is a person and a little truck. And so this is the kind of device we're looking at. This would, however, be producing 3 gigawatts of thermal power, but as you can see, rather enormous. And you might ask at this point, why can't we make fusion a bit smaller? Why is this so damn large, this thing? Well, it's because that the heat is produced in the volume and it's lost in the area. And volume goes like the radius cubed and area goes like radius squared. And so if you're too small, you just don't have enough volume to produce your heat, and you won't be able to stay warm. And this is why mammals can't be infinitesimally small. They can't be the size of a fly. In fact, the smallest mammal is what I'm showing you here. It's just barely able to keep its body temperature. It has to eat all the time, basically. And you think about a whale, and it can be in the Arctic Ocean, and it's nice and warm because it's big. So that's why we need large devices. It's to get the confinement of the heat. So is this really too large? So these are the numbers I just gave you for that rather large power plant I showed you. Well, if you compare it to the Three Gorges Dam in China, it's actually not that large. This reached an output of 16 gigawatts electric in 2009. So it's certainly not so that a fusion power plant would be too big for the electrical grid. On the other hand, it's clear that our development path towards these enormous devices will be expensive. But I have some hope there. It's being helped by some recent technological advances. The supercomputing power continues to grow, and this gives us even better optimization possibilities for the next devices. 3D manufacturing is expanding strongly. Our 3D designs are no longer at the limit of doable. Really, when we started W7X, some of the things we asked industry were at the very limits of what's ever been done. Some of them were beyond, and it was a struggle to find companies to do some of our components. It'll come back, right? And one more thing, okay? There's also been a lot of progress in high-temperature superconductors. There's a new generation of high-temperature superconductors called REPCO, which promises much higher B fields, and the magnetic field is what gives us confinement. And so if we can have a higher magnetic field at the same size, we will have a better confinement time, and we will be able to have a higher triple product, and we'll get closer to making net energy. So I hope all of these things, I believe that all of these things are going to make things more realistically achievable in the future than they were when we started out on this endeavor. So to summarize, fusion has the potential to solve the world's energy problems. With only about 1 gram of fuel present in a future power plant at any given time, the fusion burn process is inherently safe. If the plasma is disturbed, the fusion burn will simply turn off in at most a few seconds. Reaching this delicate burn process is a very difficult challenge, one that requires public support and has taken much more time than we thought originally. However, we've made significant progress and at a good pace. The progress has until now been driven by the Tokamaks concept, but the Stellarator concept has important advantages and might in fact take over in the long run. Because it has a stable, steady-state confinement of plasma, it's technologically challenging, and it must show improved performance, but we're on track to show that in W7X. And my claim is that the time is right for a Stellarator comeback. So, okay.